Hi guys, it's Miss H, and today we're going to be talking about nuclear chemistry. So when we're talking about nuclear chemistry, we're talking about changes that happen to the nucleus of the atom, changes that cause the number of protons or neutrons to change. When this happens spontaneously, we refer to it as radioactivity. The first topic we want to talk about in nuclear chemistry is half-life. Half-life is the amount of time that it takes for half of an unstable parent material to decay into a stable daughter product. So the parent material is radioactive and the daughter product is not. Here's an example for you. Carbon-14 has a half-life of 5,730 years. So if you start with 100 grams of carbon-14, after 5,730 years, you would have 50 grams of carbon-14 and 50 grams of its stable daughter product, nitrogen-14. Now you'll sometimes see this formula for half-life, but this is actually not something that we're going to be using in our class, but you've probably seen it in a math class, or if you choose to go on and take a higher level science, you might end up using this. The A with the subscripted F is the final amount of material, so that 50 grams of the daughter product in the previous slide. The AI is the initial amount of material, the 100 grams of the parent material. The 2 is a constant value, and the T is the amount of total time that has passed, so the 5,730 years, and the H is the half-life. In this case, again, it would have been that 5,730 years. Now let's take a look at some examples of the kinds of reactions we're going to be doing in this class where we're not going to need this formula, and it's a lot simpler. So here's our first example. Terbium-90 has a half-life of 64.1 hours. How much of a 100 gram sample would remain unchanged after 128.2 hours? So we're going to start out by looking here. So 64.1 hours, that's our half-life. We started with one amount of 100 grams, and we want to know how much remains unchanged after our total time of 128.2 hours. So first we have to figure out how many half-lives have passed. So we say 128.2 hours divided by 64.1 hours, and that tells us that we've had 2 half-lives. So 100 grams divided by 2 is 50 grams divided by 2 for our second half-life gives us 25 grams remaining unchanged. So again, the first thing I did was I figured out how many half-lives have passed by taking the total time and dividing it by the half-life, and then I divided it in half that many times because half-life is taking it and dividing it in 2. Let's take a look at another example. A sample contains 5 grams of calcium-45, which has a half-life of 162.6 days. How much did the sample originally contain if 487.8 days have passed? So again, we're going to start out by trying to identify some pieces here. So our 5 grams, that is our final amount. Our 162.6 days, that's our half-life. And our 487.8 days, that's our total time. So we're going to start by figuring out how many half-lives have passed by doing 487.8 days divided by 162.2 days, which gives us 3 half-lives. Now this time I know what my final amount is, so instead of dividing by 2, I'm actually going to multiply by 2. So 5 grams times 2 is 10 grams. 10 grams times 2 is 20 grams. And 20 grams times 2 is 40 grams. That's how much I started with because, again, I've had 3 half-lives that have passed, so I had to multiply by 2 3 times. Let's take a look at one. What is the half-life of technetium-99 if only 10 grams remain of a 160 gram sample after 24 hours? So our final amount is going to be our 10 grams. Our initial amount was our 160 grams. Our total time that has passed has been 24 hours. So again, the first thing I need to do is figure out how many half-lives that's been. So I need to figure out how many times do I need to divide by 2 to get from 160 to 10. So 160 grams divided by 2 is 80 grams divided by 2 is 40 grams divided by 2 is 20 grams divided by 2 is 10 grams. So that tells me that I've had 4 half-lives. So then I can take my 24 hours and divide it by 4 half-lives to figure out that each half-life is 6 hours. The other thing it could ask you is to figure out how much total time has passed by giving you the half-life, the amount of it you started with, and the amount that you finished with. Now we want to take a look at radioactive decay. So this is actually how we figure out how things have started and ended. And there's three main types of radioactive decay we need to talk about. The first is alpha decay. Alpha decay is basically a helium nucleus that gets spit out of the reaction. And so it has a positive charge that's attracted to negative electric fields. It's relatively large, slow, and easy to stop, but it can still cause burns to the skin because it is still a very high energy particle, despite the fact that it's relatively slow compared to the other types of decay. It has the Greek symbol of the lowercase alpha, and then the atomic symbol or nuclear symbol, isotope symbol, you hear any of those terms used, is 4/2He. So that's the one that we'll actually use when we do formulas to try to do radioactive decay. Our second type of radioactive decay is beta decay. It's basically an electron, so it has a negative charge. It's very small, fast, and relatively hard to stop, but usually does very little damage because of its size. The Greek symbol is the Greek letter beta, and the atomic symbol is 0/-1e. So again, the 0 is a superscript, the -1 is a subscript, and then the e is the symbol. So again, that atomic, nuclear, or isotope symbol, that's what we're going to use when we do formulas. The final is beta decay. This is not a particle, it's just very high energy, and so this makes it the most dangerous type of radioactive decay. It is very fast and extremely difficult to stop. It usually requires very thick sheets of lead in order to stop it. Unfortunately, it does not give you Hulk-like powers when you get struck with it. It can end up potentially causing a lot of damage. It usually occurs along with other types of decay, not normally by itself. The Greek symbol gamma is used for it. And then the atomic nuclear isotope symbol is 0/0 gamma. And again, that's because it's just energy. It does not have any other properties. So now let's take a look at some examples of some radioactive decay problems or balancing nuclear reactions. So what isotope is produced when radium-222 undergoes alpha decay? So 222 is my mass. Radium has the symbol Ra, and if I look at the periodic table, I see that it is number 88. So it undergoes alpha decay. So alpha decay had the symbol 4/2He. And now I need to figure out what do I need to put on this side in order to balance that out. So 4 plus 218 would give me 222. So if you think of that arrow like an equal symbol, you're trying to get the two sides equal to each other. So 218 plus 4 gives me 222. 86 plus 2 gives me 88, and number 86 on the periodic table is radon, Rn. So the isotope that's produced when radium-222 undergoes alpha decay is radon-218. Okay, let's take a look at another one. What isotope is produced when carbon-14 undergoes beta decay? Now, we already talked about this one earlier, but we're still going to go ahead and do it anyway. So 14 is the mass, carbon is atomic number 6. Okay, beta decay was the 0/-1e. So again, I'm going to think of these two sides as an equal symbol. So 0 plus 14 gives me 14. -1 plus 7 gives me 6. So 7 plus -1 equals 6. And number 7 on the periodic table is nitrogen. So I have nitrogen 14 as the isotope that's produced when carbon-14 undergoes beta decay. Here's another example. Xenon-131 is the product of the beta decay of what isotope? So now I know that I have beta decay again, and I have Xenon-131. So xenon is atomic number 54. So now I'm trying to figure out what did I start with instead of what did I end with because of this word product right here. So again, 0 plus 131 gives me 131. -1 plus 54 gives me 53. And 53 on the periodic table is iodine. Another example for us. Thorium-234 is the product of the alpha decay of what isotope? So again, we're looking for the product. So it's 234. Thorium is number 90 on the periodic table. I have alpha decay, so that's 4/2He. And so I'm trying to figure out what I started with. So 234 plus 4 gives me 238. 90 plus 2 gives me 92, and 92 on the periodic table is uranium. So this is uranium-238. Okay, one final example. How does plutonium-241 become uranium-236? Or sorry, plutonium-240 become uranium-236. So plutonium is number 94 on the periodic table. And I have 2, 3, 6. Uranium we just said was 92. So now again, I'm going to look at this. If I add these two sides together, how do I get this? So 236 plus 4 gives me 240. 92 plus 2 gives me 92. So that gives me an alpha particle. So alpha decay, alpha particle is what's produced in order to balance this out. The last thing we want to look at with nuclear chemistry is fission versus fusion. So nuclear fission is the splitting of one large nucleus into several smaller ones. This is what we do in our nuclear reactors to generate electricity. It has a lot of positives because you get a lot of bang for your buck. You get a lot of energy produced for just a small amount of material. However, it does still come with radioactive waste at the end that has to figure out how to store it. And we don't have, it does take a lot to try to produce safe nuclear facilities. The opposite of that is nuclear fusion. Nuclear fusion is the combining of small nuclei into one large one. This is what's performed inside all the stars, including our sun. This is what we'd really like to be able to do on Earth because the products are not radioactive and are not going to contribute towards greenhouse gases. But it takes really high temperatures, like 10,000 Kelvin, in order to make this occur. So when you hear them talking about trying to find cold fusion, they're not talking about like, brr, this is chilly cold. What they're talking about is temperatures that are in the thousands of degrees instead of tens of thousands of degrees. So that's basically a summary of what we're going to do with nuclear chemistry.